Let me start by saying thank you to Laurent Lies, Geotechnics Suisse, for inviting me to give this talk, where I will try to cover some fundamental concepts of geomechanics for the nuclear repository in Switzerland. So we have seen already images of this type where we are seeing one of the possible shapes of the repository. What I would like to mention here in this slide is explicitly the depth at which the repository will be constructed, which is a depth of several hundred meters. And of course, this concept of the deep geological repository is not unique. We will hear examples from other countries tomorrow, but just what I like to mention is that there are many countries in Europe specifically which are already very advanced in their repository program, and the main difference that we can see is on the type of the host rock in which the repository will be created. So some countries are going into shales and clays, like the Swiss case, but other countries are going more into crystalline rocks, especially granite. But the architecture of the repository is more or less the same. The main difference here is probably that when you have a clay, like the Swiss case or the French case, clay formations usually they are not very thick, so the architecture of the repository has to be developed mostly horizontally. This is an outline of a single tunnel for high-level waste. Once of you who will visit Monterrey will have the opportunity to see this model, and I think it's useful here to see some of the dimensions. So this is the metallic canister. You will see more or less 1 meter in diameter, which is hosting the spent fuel. This is the excavated opalino clay, and you see that the space in between the canister and the clay is filled with bentonite. So bentonite is placed both in granular form and in block forms to sustain the weight of the canister. So granular form is preferred here because it helps to minimize technological gaps between the inner surface of the tunnel and the excavated zone. Just a few words about the materials. We have heard already about opalino clay. Let me give you some more geotechnical details. So this is a sedimentary geomaterial which has a very high clay content, and it was sedimented more or less 180 million years ago. And here, let's have a look to some properties. So strength is a very stress-dependent strength, effective stress-dependent strength, so more typically of soils. And usually we have a cohesion in the order of several megapascal, 4 or 5 megapascal. Permeability is low, as we heard, so absolute permeability around -20, -21. And this fact that the permeability is low can bring to pressurization of the pore water due to temperature rise. It's a material which has also very relevant water retention capacity, so the ability of attract water and to swell. At the same time, it's very sensitive to water saturation. So if the saturation of the material is not managed in a proper way, the material will lose many of its initial geotechnical properties. Bentonite, so Swiss case is about to use MX80, which is a smectite-based clay. Essentially, we see it in granular form. This is a single grain observed at the electron microscope. And what we understand is that the structure of smectite materials is characterized of the presence of interlayer between the components of the particles, where water can be absorbed, and there is also water in between the big pores, the particles. Here are the two main properties for having a bentonite buffer. So from one side, the permeability. So the permeability of the as placed barrier, you see, is similar to the one of the opalino clay. So this ensures that the transport is essentially occurring exclusively through diffusion, so there is not advective flow. And at the same time, the ability to develop a swelling pressure in the order of several megapascal when the material is hydrated in confined condition, so constant volume condition, because this is a very good quality that the barriers to have to make sure that there is a mechanical integrity of the repository once all the supports that we can have in the early phases will have lost their structural functions. So we understand that working with these two special materials, bentonite and shales, in a system at a very significant depth, in the order of several hundreds of meters, is essentially putting us in a context which we don't find in these classical civil engineering applications, but rather not even in the reservoir geomechanics, where we tend to go to much higher depths. So we are really dealing with a kind of new branch of geomechanics that I like to call the geomechanics for repository systems. In terms of processes, there are many processes which are of interest that will take care over the long life of the repository. So first we start from the excavation, and already excavating tunnels in opalino clay means that we expose the material to air. We heard 180 million ago the material sedimented, so it means that for this duration the material has essentially been saturated underwater, and now for the first time we are putting air into it, so a lot of processes will occur, like excavation damage zone creations by the stressor unleashed, but there is also ventilation, so the material can dry, and this has to be taken into account essentially for the design of the tunnels. But we will hear about this in the presentation today. After the barrier will be put in place and the system will be closed, there will be the hydration of the barrier from water coming from the surrounding rock. So swelling pressure will develop, technical gaps will be closed. And at the same time, the system will have its non-isothermal phase, because heat emitted by the waste will increase the temperature of the system. And at a very late time, there will be also, as we mentioned before, the gas generation and migration problem. So corrosion of different materials which are in the repository will generate gas. So mass of gas is created in a very compacted space, so a lot of volume is available for the gas. So this will result in the buildup of gas pressure. So those are the main, I would say, aspects that we have to take into account in our geotechnical analysis. But also from a geotechnical or geomechanical perspective, there is also something which is very unique, I think, in this field. It's really the need of linking different observation scales. So starting from understanding and quantifying physical mechanisms really at the micro or pore scale, and then moving to the elementary volume scale in which we are testing the material. So those are the sizes that we usually use in our labs. And of course, this is where we derive constitutive model and material parameters. And then a lot of efforts are being done in the building of, I would say, intermediate scale models, the so-called mock-up test, in which we can validate not only the constitutive models, but also the modeling frameworks. And then, as also I think we will hear today and tomorrow, a lot of full-scale experiments have been already started. Of course, in those experiments, there is no the real waste put into place, but those are mostly done with heaters, electrical heaters, to simulate the thermal wave into the system. We understand that now our geomechanical framework has to be extended in what we call the multiphysical geomechanics. It means that we have to account for many variables that we don't consider in classical geotechniques. So classical geotechniques is essentially based in HM or hydromechanical formulation. This is why you can solve all your consolidation problems, for example. But as we move to the nuclear waste repository, so we understood that we need to include temperature, of course, the mechanics. We have the hydraulic part, the flow part, that now has to account for the presence of two fluids, so the water, but also the gas that it is going to be generated. And I didn't mention it explicitly, but there is also a part related to chemistry that I'm not mentioning today, but one also may want to account for possible changes in the chemical composition of the pore water in the long term. So those variables, temperature, pressures of fluids, confining pressure and chemical, are not only needed to be accounted for, but also their ranges is quite large, so which makes also our analysis specifically interesting, because temperature can rise. There is not yet a fixed final level of temperature which is allowed, but easily we can be around 100 degrees. Pressures, we are at very high depths, so pressure of the water will be high. At the same time, pressure of the gas, as we will hear, can be high. But there is also the suction domain where the pressure of the water is negative, especially as a consequence of the excavation. Confining pressures quite high because we are at depth, and also chemical loads can involve changes in pH, and also changes in the osmotic suction. Okay, so this was an introduction just to set a little bit the ground for this presentation. Now I will present briefly some of those aspects, how we are dealing with some of those aspects, and we will start with some hydromechanical behaviors. And the first thing I would like to point out is about the difficulty in working with the Opalinus clay samples in the lab. So let's say that we start from a sample which is under positive pore water pressure. By the way, those numbers make reference to the Monterrey setting. So you had the pore water pressure is around 2 megapascal, so it's positive water pressure. As soon as we extract samples from the ground, we will generate suction, so we will generate negative pore water pressure simply coming from the excavation. But there is more, the samples then have to be confined, sent to the lab, and this operation is progressively desaturating the material, and as a consequence we are increasing the suction in the material. And finally, when we have to test the specimen, we have to prepare it. So usually this operation takes time, the sample has to be worked, and this will result in further desaturation of the sample. So essentially, when we are ready to perform a laboratory test, we are here, while we would like to have information for this state here. So the resaturation phase is quite a critical phase. Just to give you some quantitative information on these processes, those are suction measurements that we have recently carried out in one of the deep boreholes. You see, this is the suction of the sample just after the retrieval, so this is just after the excavation. And at the time we took the samples, even if they were well preserved to the lab, the suction has already increased. Now, suction, so it's important, and if we don't account for the presence of suction in our soils, we can really have a bad estimation of the mechanical properties. This is just an example where we are testing in unconstrained compression test Opalinus clay sample, where we are controlling the suction by controlling the relative humidity in this closed chamber, and we see that the Young modulus of the Opalinus clays is very sensitive to the suction that we are applying. So if we are not able to control properly the state of the pore water pressure in the pores of our material, we can have a severe, I would say, problem in estimating the stiffness of the material. So what we do, we usually resaturate the material before we do the test, and now we have learned that the best practice is to resaturate materials, essentially keeping their volume constant as you would do in a constant volume swelling test. And just to give you an example of how important the swelling it can be in this material, those are two practically identical samples of Opalinus clay that are let to swell before they are compressed at two different stress levels. So you see the stress levels are quite low. Here we are talking about a few dozens of kPa, here just some kPa. You see how much the material can swell you see how much even few kPa of confining stress change completely the response of the material. But most importantly, if you would like to derive the preconsolidation stress from those curves, for example by applying the Casagrande construction, you would read effective stresses which are impossible for the history of the material. So this swelling, which if the swelling is allowed, essentially we are erasing almost 200 million years of history of this material, and the mechanical information that we can get from testing is quite limited. The reason is quite obvious, is because those materials have bedding planes, and as soon as they hydrate without confinement, those bending plates can open, so reducing all the mechanical properties of the material. And this has been also quantified in terms of strength. One of our recent works where we are showing that the triaxial shear strength, so the envelope essentially for the damage samples, damage here is induced by swelling, so the swelling was allowed for those tests. But you see how the envelope, the envelope is shifting by reducing in a very important manner the intercept cohesion of the material. Another aspect I would like to mention is about consolidation. We understand that these are materials a little bit in between soils and rocks, but they consolidate mostly as a soil. But the stress levels that we need to reach for testing the consolidation behaviors is not the one that we have in conventional edometric tests. So this is why we have developed our high stress edometric setup. With this stress, we can go up to 100 megapascal of confining stress. And when you analyze the consolidation of these materials, you have also to include possible poroelastic features, because your BO coefficient cannot be 1, especially for the high stress levels. So the Terzaghi effective stress has to may not work. So you need also to include the BO coefficient here. And this is our definition of the BO coefficient that we can derive from an edometric test. But if you assume isotropy of the material, essentially it's the same value that we get from the isotropic case. And so the consolidation of these materials follows, I would say, quite usually the usual curve that we know from textbooks for soils. Here, the only difficulty is that it's very hard to apply instantaneously high levels. So usually all the systems at high levels, they have some delay time in the application of the load, and this is why you don't get the classical S shape, but you get a double S shaped. But this has been accounted in our theory for the consolidation of opalinous clay, and thanks to this type of analysis, we can get very nice and comprehensive information on the hydromechanical behavior of this material under compression. So we have the classical edometric curve, but for each step, we can provide information on the stiffness, on the consolidation, on the secondary compression, so for the creep behavior, and also for the BO coefficient. So this type of analysis has been used extensively for many years now for materials coming from different places and different boreholes. And so we are now very able to read the compression behavior of these materials coming from different sites, taking into account the specificities of the site. And we understood that essentially one of the key elements that can be used to group together tests done from different sites is the clay fraction. So in one of the reports that will be available very soon, you may find pictures of this kind where you see some of the compression parameters as the swelling index are beautifully plotted as a function of the clay mineral from tests done at different sites. Quickly about the thermomechanical behaviors. We have heard about already this morning. So from one side, I think there are two main features from a geomechanical perspective to be considered. From one side, there is the possibility of overpressure induced by thermal load This is the mass balance of water. If we think about undrained conditions, so we neglect flow and we neglect volume change of the material, and we can also neglect compressivity of the grains for a second, we realize that the thermal expansion of solid and liquid phases will generate pressure. And this effect is not, cannot be marginal, and has been also documented. This is one of the experiments done in Monterrey, where you see the thermal pulse that was applied in an heater and the consequent rise in pore water pressure that can be in the order of several megapascals. The other aspect that I would like to mention is about, speaking about thermal behavior, is about the non-isothermal behavior of the Opalinus clay. So we have our device in which we can test the materials also applying temperature changes. And if we now plot our stress paths, so we have the control of vertical stress, but also the control of temperature. It means that we can test the axial or the volumetric response of this material based on temperature variations. And we understand that this material is following the classical thermoplastic behavior, where essentially if the material is heated at high overconsolidation states, so it means at low stresses with respect to the yield stress, the material is essentially expanding and compressing. By when it is heated in a normally consolidated state, the material can undergo compaction, which results to be irreversible. So there is thermoplasticity also in Opalinus clay. I like to mention here, probably I'll take 30 seconds just to say that this fact that thermoplasticity is a very important phenomena was already detected by Casagrande in 36 when he was explaining how to get the preconsolidation stress. He was advising that if you test the material at a temperature which is higher than the one of the ground, the virgin compression line moves to the left. So it means that you are decreasing your preconsolidation stress. And so this very early insight is at the basis of our common understanding of thermoplasticity. Because essentially in thermoplasticity, what we do is that we decrease the yield stress with temperature, so that when we heat the material in normal consolidated state, the material is essentially moving the yield curve, so it's hardening the material, and so a plastic strain is produced. While if we do the same heating far from the yield curve, the behavior is essentially elastic. Quickly about the gas transport. So gas transport was mentioned today. There are already quantifications of in scenarios how much gas can be produced over the course of the year. So this was done by Nagra, and you see the cumulative volume of gas. And now the big problem is how this gas can escape from the system, because if we don't take care of the gas release from the system, essentially we are creating a forgotten bombs under our feet. So there is a lot of research which is currently done in this sense, and there are several mechanisms of gas transport in shales that have been identified. The gas can move just by diffusion, or it can move in a two-phase flow configuration, so where water and gas are moved together, and it could also create some dilatancy pathways, but in the worst case, if the gas pressure is too high, can even fracture the formation. So we have quite active at EPFL in this sense. We have our testing device where we can inject gas at high pressure, and we can assess how the material is behaving mechanically. So essentially by monitoring the strain field of the material during the gas passage, and highlighting in this case that the two-phase flow is essentially, for this setting here, the mechanism which is driving the analysis. Very quickly, I just want to say that all this knowledge that we have seen has to be used to make long-term predictions. So I will just present a very briefly an analysis that we have done on the long-term evolution of the barrier. So this is done taking into account the specific features of the bentonite, especially knowing that the bentonite is a multimodal porous material with pores in between grains and pores in the grain. And this has to be taken into account, for example, when we write our constitutive law. Just quickly, this is our water retention curve, where we can separate the water which is stored within the smectite particles and the water which is stored in the free pores. And this has to be included in a mechanical framework where we are using, in this case, the extended effective stress for unsaturated conditions. And you may recognize the Hill stress curve that we have seen before for temperature. We have also something similar for accounting degree of saturation, so partial saturation. And this, of course, is implemented as a constitutive model. You may be scared by the number of parameters that you see in this slide here, but I just want to ensure that all these parameters have a physical meaning, so we can design experiments to get them. And the constitutive model is usually implemented in a finite element code, where we are essentially solving the balances of the solid, the water, and the gas phase together with the energy conservation equation and the classical equilibrium equation. So we can run our finite element simulations. This is one case that we have conducted with NAGRA, where we are assessing possible effects of the homogeneity of the barrier. So in one case, the barrier is put at a constant dry density of 1.5. In the other case, we are assuming that there is segregation of the granular bentonite. So there is a profile, of density at the beginning, and then we simulate the behavior of this material, accounting for the hydration and the temperature rise. Let me just skip to this one. And we can have understanding of evolution of the density of the barrier. So this is the case where the material is homogeneous. We understand that more or less in 100 years, the degree of saturation will be 1, so the system will be fully saturated. And you see that there is a good homogeneity of the density of the barrier, which is also the case if you start from a segregated case. So if the density is not uniform at the beginning, there is anyway at the end a very good homogenization capacity of the system, and end up in a density which is more or less similar. Okay. And this is all what I wanted to present. So I try to convince you that the geomechanics plays a very fundamental role in the designing a long-term safety assessment of the future Swiss nuclear waste repository. Multi-physical couplings are really the key, so they need to extend classical geomechanical formulation to account for other variables. And over the past decades, there has been a very significant advance, I would say, in both in experimental techniques and in computational modeling capabilities. And I really believe that now we have the tools and the fundamental understanding to be able to make a realistic long-term prediction for the safety of the repository. And with this, I thank you for your attention.